presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on elastic behavior. In the last lesson, we learned about the different types of deformation, tensile stress, and tensile strain. Today, we will study Hooke's law, Young's modulus, and the uses of a stress and strain graph. We have a lot to discuss today, students. So let us begin. Observe this graph. The plot shows an extension of a copper wire against an applied load. As you can see, the graph starts in a straight line. Over this range, the extension will be proportional to the applied force. Point A on the graph marks where the load begins to increase and is known as the limit of proportionality. The yield point is reached at point B, where there is a sudden increase in extension. Point C marks where the wire cannot take any more force and breaks. The correlation between extension and applied force is known as Hooke's law. It was named in honor of Robert Hooke, the English natural philosopher. Hooke's law states that strain is directly proportional to stress. It is formally expressed this way, where x is the displacement of the wire from its equilibrium position, F is the restoring force exerted by the material, and K is a constant called spring constant. For small loads, notice that the extension is elastic. For large loads, the spring suffers permanent or plastic deformation. In this video, the experimenters cannot know the exact load for which the elastic behavior ceases, and the spring enters the plastic region. The only way to tell is to remove the load and see if the wire completely recovers. You can be sure that while the spring is in the Hooke's law region, also called the elastic region, its behavior is elastic. When the yield point is reached, it may be assumed that layers of atoms have slipped over one another within the metal, and the spring will suffer a permanent extension. If too much force is applied, surpassing the breaking strength of the material, the spring will snap and the experiment will be over. This is another stress-strain graph, students. Teacher, please form the students into groups of 3 to 4. Students, please demonstrate your understanding of these terms by making a rough copy of this graph and labeling each of these points and regions. Please get started right away.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. Did you manage to draw and label your graphs in time? If you did, they should look something like this. Good work, students. Teacher, please collect the students' graphs at the conclusion of the lesson and make sure that everyone understands the terms we have learned. We now understand Hooke's law, which states that stress is proportional to strain. In the case of a length of copper wire, if we need to measure how easily it stretches, we take the tensile stress divided by tensile strain. This is another way of expressing the stress that would have to be applied for each unit of strain caused. The ratio of tensile stress to tensile strain up to the material's limit of proportionality is called Young's modulus. In symbols, it is expressed like this. We can rearrange it into the more elegant form seen here. Young's modulus is expressed in the units of stress divided into the units of strain. Since strain is without a specific unit, we will use the same units as stress, newtons per square meter. Students, please note that the unit measure is called the Pascal, which you may remember from grade 9 physics lessons on pressure, is another way of saying newtons per square meter. We will be using pascals in some of our lessons in the future, so please remember that they are the same thing. It is time for another activity, students. We will solve an extension problem using a Young's modulus. Let us say that a 3-meter long steel wire has a cross-sectional area of 4.1 millimeters squared. It hangs from a tall support, and a load of 500 grams is attached to its end. The Young's modulus of steel in this example is 2 times 10 exponent 11. For this equation, F is the weight of the 500-gram load, which is half a kilogram times 9.8 newtons per kilogram. This means that F equals 4.9 newtons. Another way of expressing 4.1 square millimeters is by saying 4.1 times 10 exponent negative 6 meters squared. Given these facts, by how much will the steel wire extend? Please get started on this problem now.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, students. I hope you did not have too much trouble with this problem. The solution is actually simple. Remember that our formula for Young's modulus is tensile stress to tensile strain, which is expressed this way. Therefore, finding our answer is a matter of rearranging the formula and substituting the proper values. First, we restate our formula to solve for x. Next, we enter our values. The products of our multiplication yield an answer of 14.7 over 820,000. This is better expressed as 1.79 times 10 exponent -5 meter, which is the value of x. This is how much the steel wire will extend. If that was your answer, great work. If you did not get this answer, or could not correctly apply the Young's modulus, do not be afraid to ask teacher for help after the lesson. Students, Young's modulus is not only helpful just for calculating extension. We can also use it to compare the elastic properties of different materials by comparing the Young's modulus for each. For instance, the Young's modulus for copper is approximately 117 gigapascals. Compare that to steel, which is rated at about 200 gigapascals, or tungsten, which is about 400 gigapascals. That is all for today's lesson, students. Today, we have learned about Hooke's law, stress and strain graphs, and how Young's modulus may be used to measure the tensile strengths of different materials. Thank you for joining me today. Until next time, thank you, teacher. Thank you, students.